We're back here. I was doing something before. That neural network. Nope. We're adding something. No scaling. No, we are adding something in neural network. Neural network add layer null. Okay, add layer pooling. Add layer convolution. We need to add a convolutional layer. Add layer convolution. Let's create a convolutional layer first. Where was I? Yeah, create a convolutional layer first. New file. Virtual file. Okay. Let's just copy. Which one? Type layer scaling. Copy. Now Control All. Copy. And paste. Layer convolution. I started doing this before, but I didn't finish it. I think I lost all the file. Okay, convolution. Could I know layer convolution? Convolution is rather more complicated than everything else. Convolution. Okay. Okay, here we don't need result because the source of the size of the file has to be the same as the size of the next file of the next layer. I mean, the source size of this layer on side longs with height depth. We don't need anything else here. Actually, let's keep this here. Now we need something else: filter width and filter height. Now filter width, filter height. For other things like at-root convolution, we just no wait. Okay, next filter width, filter height. Do we need this? No, I don't think we do. Or do we? Yeah, I think. Yeah, maybe we do. Okay. Neural layer create. That's this. Okay, set the layer to convolution. Just set everything correctly. Convolution. Convolution. Okay, what else do we need? Type shape assign. Do we need this? No. Or maybe we do. Neural array create. Okay, bias. I'm just copying for bias. Okay, we need to create several things here. Copy several things. Create parent.layer weights, parent.layer vectors with height depth, but that's not enough. That is not enough. Okay, something else we need to create. Vectors. This is not working. I'm missing something because that's not with height depth. That can't be right. Okay, now I got it. Okay, it is with height depth, but something else that we need. Okay, the weights and the vector has to be the filter height. Width, height is filter width, filter height. Ah, now I remember. Filter width, filter height. That's the same. Filter count. Now we need to calculate filter count. Filter count equals. Okay. Oh, now we have a problem. Now I remember. It's all more complicated than I thought. Yeah, I thought we were done, but we're really not done. In order to calculate the filter count, we need to know the length of the next layer, which means that we have to copy the whole thing again. There are better ways of doing this, but having this many parameters is just annoying. Okay, we need size of the next layer equals result depth. Most of this we're not gonna need, but just to be clear, just to be sure, we're just going to include it. Result depth times result depth time source depth. The number of filters has to be equal to the number of slices in the source times the number of slices in the result. Unsigned long. Result filter depth, filter count. Okay. Filter count. Anything else will be checked in the array. Okay, filter count, source depth at result depth. Okay. Now, we create the weights and the vectors. We need something else too, but I don't remember what it was. I'm sure we need something else. Filter count. Time filter count. There's other things we need to add, but if we need to add it, we can just copy this spot right here. So it's probably not important. Okay, create index map. Which index map do we need? Convolution 2D. Create a convolution 2D. Source filter. Source result filter width filter height. Convolution 2D. Source parent.layer map 1 index map 1. Okay, where did I come up with that? Neural network, neural array, index map. I was copying something. Yeah. Need to keep track of what I'm doing. Okay, I keep getting lost here. Is result, source, result first, source second. Okay, result, source, source width, source height 1. Oi. Oh. No. They should both be the same, I think. Index map. Oh no, we need result width. If they're not the same, then we have a problem, maybe. No, we have a problem. We're just going to use result width, because assuming that the source is larger, then that will create a slight problem. Okay, result is result shape. Result. Or maybe not. Okay, now I'm confusing myself again. Oh my god, I'm just confusing myself again, because if it is this, if they're not the same size, then we need to know that. Source result. If they're not the same size, we need to know that. Result source. Yeah, whatever. Just in case, I'm going to include both. Convolution 2D. We're missing something here. Filter width, filter height. Okay. Let's copy it. Filter width, filter height. Just copy this. We don't need anything else. And there we have it. Okay, that's the first one. Now we need the second one, because we have to do convolution forward and convolution backwards. And convolution 2D transpose. Convolution 2D transpose. Everything else is the same, except we reversed result by source. At least I hope that's how it works. If there's a mistake, we're gonna have to chase it down. Okay, index 2, next, parent, result is result width, result height 1. Just make sure we're getting everything right here, because we don't want to mess this up. Create convolution 2D, create convolution 2D transpose. Okay, source, filter width, filter height, everything the same. Yeah, so far so good. Okay, so far so good. Convolution feed forward. Convolution feed forward is, yes, for convolution feed forward, we have it right here. I have trouble finding it. Okay, it's result, source, filter, and index map. Okay, result, source, filter. Result is next to the output. Source, parent.output, filter equals parent.layer weights. Simple. We just copy everything. Weights. If something goes wrong, the the function checks everything anyway, so let's make sure we check everything. Filter count equal result count at sums count. Index map the next equal result length. Index map the result high filter length. And that should be everything, I hope. Filter length. How about filter width? Nah, that doesn't matter. Even if it's wrong, it's just gonna not do anything, so we don't need to check. Okay, index map, bind layer weights, and convolution to the forward. Now, for convolution to the reverse. It is almost the same, but slightly more complicated. Reverse. Okay, let's see what's different. Convolution to the reverse. Source filter, result filter, index map. Actually, it's exactly the same, but just in reverse. Okay, so we didn't miss anything here. Reverse. Let us make sure we got everything right. It's next. Do we have everything in the right order? Now we need everything in the same order because it's forward and then reverse. Everything needs to be in the same order, but we call deltas. The next, then parent weights. Next dot layer deltas. For backpropagation, we backpropagate to the deltas, and the weights are the same, and layer map 2, so it's transposed. But we're still missing one very important function, and that's the big one, the one that's really gonna hurt. Okay, where is it? Okay, neural network that layer pooling, backpropagate, update weights. No, not pooling, bias. Update weights. This one I have no idea how I'm going to do it yet, but we can figure it out. It's relatively simple. Still very complicated, but doable. No, convolution, not bias. Convolution, backpropagate, neural network, convolution, update weights. Everything's the same, so now get rid of that. We're not waiting for that yet. Convolution to the reverse. Everything's the same. Nothing's different. Okay, now for the hard part. No, the convolution. Yeah, don't forget that. Actually, not even the hard part right here yet. And bias also. Bias. We need to destroy layer and weights. Make sure we do everything in the right order, otherwise we could have problems. Parent dot layer weights destroy parent layer of the. Oh. And now I forgot something really important again. Index map destroy. We need to destroy the index maps. Okay, let's go back. Pooling. Destroy. Index map destroy. Which ones? Oh, come on. Parent dot index map 1. Not parent. Come on. And parent dot index map 1. Parent dot index map 2. Copy, paste. Parent dot index map 2. We have to destroy both of them, because if we allocate something, we have to deallocate it. Otherwise, you have problems. Bias doesn't have an index map, but scaling does. Scaling have one of them? Oh yeah, it has two of them. Okay, index map 1, index map 2. Okay, everything's the same, I think. Yeah, there's no difference anywhere. Pooling create. Wait a minute. Why is it creating only one? I can't remember why. Oh, because it does forward and reverse. We don't need both. Pooling only has one index map created. Convolution is two index maps because when doing convolution, we have to do a transpose convolution. So that the transpose convolution requires a different index map with the indices in different orders. Okay, now save it. Tap neural layer convolution. No. Layer convolution. Come on, stop doing that. Convolution.h. Okay. Everything's good, I think. Filter count. Type shape assigned. Source result. Source result. Result source. It's probably not going to be needed, but just in case. Okay, now for neural network. Neural network. Add layer. Add layer pooling. Add layer convolution. Convolution. Source width, source height, source depth, and filter width, filter height. That's a lot of variables. I really hate that. Filter, get out of the way. Filter width, filter height. Filter width, filter height. Okay, add layer convolution, add layer convolution create. Convolutional layer create. Okay. Yeah, whatever. Return tap neural layer convolution create. Is there something missing? Tap neural layer convolution create. I don't know. Seems to be is undefined. Did I mistype it? Ah, whatever. I think maybe I mistyped something. Convolution create. Maybe I mistyped something. Ah, filter width. Filter height. Oh, of course. I did not include that in the list of includes. Convolution. Neural layer convolution. Okay. It's just ugly. Why is it still complaining? Yeah, it's still complaining about something. Oh no, now it's good. Okay, now same as always, we copy this convolution. Convolution. Just copy this here. And where are layers? What do I have layers? No layer. And then add it to list. Of enumerates. Okay, now we're good. Neural network. Oh, there we are. Convolution. Copy. Convolution feed forward. Okay, we're just going to make everything as consistent as possible to avoid hurting ourselves. Nope. Pulling convolution backpropagate. Convolution backpropagate and convolution update weights. We need that. No layer convolution. Convolution update weights and convolution destroy. Convolution destroy. Okay, so far so good. Now for the big one. How to update weights inside the convolution. Okay, matrix forward, matrix reverse, matrix update weights. Okay, now we're gonna do matrix update weights and then we'll convert that from matrix into convolution. Okay, first of all, figure out how everything works. Okay, matrix what? Matrix update weights. No, matrix update weights doesn't really work. We need to get the derivatives first. Matrix. Wait, am I in the right place? No, matrix forward, reverse. No, we have a second reverse. Matrix get derivatives. We need to get the derivatives and then add them to the update, because the update momentum requires a set of deltas, and we don't have that yet. Okay, deltas and alphas. Okay, result source filter and result source filter. What else do I need? Result source filter. Result source. Result source deltas. Not deltas. Yeah, deltas derivatives. That's the null raise. That's the result. We take the source, the result, and the filter, and then we figure out how to get it into. I can't remember how I did that. Oh, now I get it. We have to multiply something by something. The source by the corresponding result. Yeah, I'm trying to figure out, remember how I did that. Anyway, let's just do it and see what happens. Okay, deltas, not weights, deltas. Okay, if deltas, everything should be exactly the same. Okay, for I, for j. Okay, for I, for j, we need to multiply something. Okay, k times j. No, whatever. Okay, let's just do what it is. Okay, source times. I know that it's source times result, but I don't know which source and which result. Okay, it's source times result something. Okay, it's filter. Filter. Filter dot k times filter dot array data. Filter dot array data dot k equals result dot j times source dot I. Now I remember it. In order to get the derivatives, you have to multiply the previous deltas by the source. Just call it something else. The names are really confusing. Okay, derivatives. It's called derivatives, deltas, outputs. Because otherwise the names start to get really confusing. Outputs, deltas, derivatives, the result. Okay, outputs, deltas. Oh no, let's call it deltas first. Outputs and derivatives. That's a better name. Okay, if derivatives dot array length not equals deltas dot array length times outputs. Okay, that's how it works. You multiply for each delta in the result, you multiply by every single one of the outputs. For each delta in the result, we multiply by every single one of the outputs, and the result of that is the derivative of that particular of the corresponding weight. Okay, because we're doing a two-dimensional thing. K equals, for a source derivative, k equals I. Everything's pretty much the same mostly, but I can't remember which is which. Everything's, wait a minute, source? No, not source, deltas. Not deltas, outputs. Wow. Outputs dot array length equals deltas dot array length. Okay. Filter dot array data plus k, not filter, derivatives dot array data dot k equals deltas dot array data j. J is always the result, the next layer, the array, the outputs of the next layer, and outputs. Oh, not so hard. K equals outputs. It's a two-dimensional array, so outputs. It's important to get this in the right order because everything has to be the same size and shape as what you do here. So everything has to be in the right order. No, we don't need that. We don't need that here. Okay. So that's it. That's actually it. Okay, for each in the two-dimensional, the derivative is a two-dimensional array, and the outputs and the deltas are one-dimensional arrays. So for each item in the deltas, we multiply by the by every single item in the source in turn. Okay, it doesn't matter if you get in the right order, just as long as I equals x and j equals y, the y-axis. And we could not exchange j for I here. It would not work right. So far, yeah, that's it. Next, we convert all of this into a convolution operation, and that's going to take a long time. So let me pause and see if I can figure out how it works. Okay, the first step is just copy this part right here, convolution 2D. Everything is basically the same thing, so we're going to copy it and then modify it into what we need it to be. Okay, get derivatives. It's a long name, but we're trying to be clear. Okay, deltas, which means the final deltas, outputs, the output of the parent layer, and derivatives. Okay, and index map. Okay, same thing here. If deltas, would it make sense to just keep the names? Let's just keep the names, because changing name doesn't make it that much clearer. Having to modify everything here every single time, we just need to know what is what. Result. Changing name doesn't make it that much clearer, so let's just know what we're doing here. Okay, so everything as before, from source count, result count for each pixel. Now what? Okay, before we begin, let's just define exactly what we need to do. Okay, this is a copy of the convolution reverse. Everything is the same, but and here's the convolution get derivatives. What we need to do is replace this with a convolution operation, but not exactly a convolution operation, because instead of multiplying source by result, source by filter and storing result, we're multiplying result times source to get the filter. So basically, we need to reverse over convolution operation where we put the results inside the filters. Now I need to figure out what that actually means. Okay, that's gonna take a few minutes or a few hours. Okay, I think I got it now. Okay, that took a while. All right, let's figure this out. Okay, we had this up here, convolution value, and we had this thing called index offset, which was think of the index map as a two-dimensional array. The index offset is a specific column in that index. But down here we do something slightly different, because we need to figure out the derivative of each individual pixel in each individual filter. So the number of filter is width is the number of source slices, source images, times the number of result images. So 10 by 10 will be 100, and each filter has a something like 3 by 3 pixels, so 900 pixels. So here we need to figure. I've changed something to specify one specific pixel in one specific filter. Okay, that specific pixel in that specific filter, and in order to get the derivatives, we have to multiply that pixel. We have to do the convolution operation for that pixel alone. Normally, when we do convolution operation, we multiply every item in the filter by a corresponding item in the source, and then take the final result and put that in the result image. But here we're doing something that's slightly different. We are starting with, okay, it's a row, it's a series of columns. We pick a specific row from top to bottom. We pick a specific row, and then we set j to the specific index in that particular column. and then down, and then we increment, and then down here we just go horizontally in for each individual index in that column, and then each individual index also happens to correspond to a particular pixel in the index array. So we're going to every pixel in the index array. So we're doing the full convolution operation for each individual pixel in turn. This may or may not be the fastest way to do it, but really, there's really no other way to do it that's faster, unless we go the reverse and just add and then do multiplication and division, and that's just complicated. I never really checked which way was faster, but so far it looks like this is the fastest way. So we're going to each individual pixel in each individual filter, and then multiply, and then doing that operation back here, taking the derivatives, result, that particular result at the source index times the specific source pixel that is specified in the index. Okay, so we're doing the that's my interpretation of the reverse onto convolution operation. Then we take the sum, and then we don't need to return the sum. There's a filter. Filter. We don't need to return the sum. Filter dot filter offset. No, not filter offset. Filter dot filter index. Filter index plus filter offset. No. What am I doing? Filter offset. Filter index plus filter offset equals sum. All right. Not return. We don't need to return. We don't need to return anything. Void. Okay. What? No. What's wrong? Okay. There's a lot going on here. Okay. For each pixel in the index. No. For each pixel in a particular row. Now, each row corresponds to a particular filter. Now, for a particular pixel in the filter, each row in the index map is a particular row at a particular pixel in the index map, and every a pixel in that row equals an index into the source, and the position of that pixel in the row correspond to a particular pixel in the result. Okay, so we multiply them both. That gives us the derivative right there, and we sum them up. That gives us the sum of the derivatives for that particular filter index. Okay, it took a long time. I hope I got it right. If I didn't, then we just have to do this again, and until I get something that works. Okay, now let's get back down here. Okay, we don't need that here. Okay, here for ij, we need to move that up here. Okay, for every pixel. Okay, for every pixel in the source, for every pixel in the for every image in the source, for every image in the result, and now we will go to each individual pixel in the not index length. Now I remember what I need to remember what this means. I'm getting lost here. Okay, now I remember. For k equals each individual in the filter length, not source length, filter length, because we updated in the filter. Okay, filter length. I think everything else is the same. Filter length k. Same thing, but now we change this to k. Convolution add. No, not sum. We don't need sum. Index map convolution add. Result source. We need source and filter. Is it result source filter? Yeah, it's result source filter. Result source filter. Okay, result source filter. What am I missing? Index map, index width, index height, index data. Result width, result height, result filter. Okay. Result source times j. We need the source. This is just housekeeping. I hope this works. Source height plus j. source length times j. The source, okay, filter length times j times source cat plus I. So the filter arrays are two-dimensional, the other arrays are one-dimensional, and that, no, we don't need that one. Tab. Okay, we don't need that one. Okay, IJK filter length. We need to go to each pixel in the filter, and hopefully that's it. Okay, I'm gonna do a once over, make sure I didn't miss anything. Okay, I'm fairly sure I got everything right. Okay, now let's go back to the convolution layer and do some updates. Okay, kernel convolution get derivatives. What do we need? Oh, what do I need? I keep forgetting what I need. Oh, result source filter. Okay, result source filter. What is needed? Result is we need some place to put it. Result is next dot layer dot layer deltas. Next dot layer delta. That's the result. Source is parent dot layer outputs. Copy. And result is parent dot layer. Okay, it cannot be weights. What else is it? It cannot be weights. It cannot be vectors either. We need another. You need another array. Okay, new array create vectors alphas. No, alphas. No, alphas. It's an identical copies to weights. We have delta, so we have alpha and beta. That makes sense. Okay, weights, deltas, let's just add it here. Alphas. Okay, everything is set to 0, so we don't have to worry about setting this up. Okay, convolution, we create alphas, we need to destroy alphas. Oh, did I forget? Wait, did I forget to destroy the... Oh, I did. Oh, we forgot to destroy the index map. Index map 1, index map 2. Yeah, I forgot to destroy in deltas. I mean bias. Yeah, it's here. It's been destroyed. Okay. Okay, now we create the alphas. Get derivative alphas. Okay. Now we're good. Get derivative alphas, and what else we need? Index map, yeah. Okay, their derivative uses index map 1. Okay, and that should be it. Shouldn't it? Index map get derivatives. Result, source, filter, index map. Yeah. So what is it complaining about? No, it's not. It's good. Okay, we got the derivatives, and now we update momentum. Everything should be the same. Layer weights, vectors, and alphas. So far, it's looking good. Just save everything and rebuild. Oh, what's that? Didn't save. Oh, okay. I didn't add it to the list. Add existing item. No layer convolution. Okay, we built. Let's just hope it doesn't start complaining again. Okay, so far so good. Wait, it still didn't save. It still didn't do it right. Rebuild again. Okay, I think I got it right this time. Okay, now let's change this to convolution. Wait. Oh, here. Add layer convolution. Convolution. Oh, what am I doing? Convolution. Tweet. No. Everything's the same, so we don't need to worry about that. Just copy. Add layer convolution, twee by twee. All I can say is it's going to be very, very slow. Let's see what happens. Oh, wait, one more thing. Just like with bias, we have to randomize. Fill random. We need to randomize. Fill random weights, fill random vectors. Fill 0 vectors. Okay, alphas. Yeah, alphas don't matter. There's just get used once and then never again. Okay, build, we build. Let's just see if it works. No, it doesn't. No, cancel. Cancel. We save. And no, what is it doing? Here, save, and we build. Okay, we have 2 layers, the null layer and not null layer. We just have to see if it works. If it doesn't, we are in trouble. Yep, turns out I made a major error. It's right here. When we add up all the sums, the result turns out to be something enormous. Because we're taking the derivative of a lot of filters and summing them together. And what I forgot to do is that you're supposed to divide. Counter. We need a counter. We need to take the average of them. Because if you take the total sum, then it's just going to equal something ridiculous. Counter equals 0. Counter plus plus. Okay. If counter more than 1, which it has to be, sum div equal counter. Well, yeah, that may not be safe. Sum equals sum divided by counter. Okay, that should do it. Build, rebuild, see what happens. That's an obvious error, but it's a tiny one. Things could have gone really bad. Okay, so it seems to be working. Yep, it's working. We can see it right there. It's working. Oh, that was great. It's working. It goes from really blurry, we've really messed up, to better, to moving toward what it's supposed to be. It's not working well, but it's definitely not fast. But this is to be expected. This is to be expected. But the good news is it's doing something. I'm going to keep checking it to make sure that it's working properly instead of just doing something random. Okay, so far it's working generally well, but not perfect at all. It's kind of messed up. So next time I'm going to do a few little things to get it to work better. It's not going exactly the way it's supposed to, but doesn't look like there's any errors. So far so good. We're gonna make things better next time.